Course. Ow. Now I'm having the day already. I have to go to a work function tonight, and I had enough points where I could get a hotel because the work function is like almost 2 hours from where I live. So that's why I like hotels.com. They had points. Yeah, they do. Let's see. Did this work? Thought I pressed enter. Please don't tell me that Canvas has decided to go out. I mean, okay. Well, that sucks. Is it even moving? The browser's not even moving. That's streaming. So I know the internet's there. All right. Ah, come on, catch up. So while that's going, I'm just going to pull up a search because that works. Maybe the servers don't. So let me pull up some images, some examples with structures. Here we go. This is what I was looking for. I like this image. Okay, so I made the mistake of putting a hydrogen on one of these while there was a charge. So we have to remember that when we're dealing with a skeletal structure, let's say it's like this. We'll just use this as an example. And I got something here, and I've got a charge right here. I have a positive charge on this carbon right here. What this looks like is actually this. So we've got H, positive charge. And then we've got C, H. We got a C here, H, C, H. Like that. So what's happened here, when we have a positive charge on this carbon, whenever a reaction happens and we end up with like a halogen or an oxygen or something like that, when it takes all of the electrons in this bond, it can also take the electron from that carbon. So normally, carbon has 4 electrons in its outer shell, right? So if this is here, and let's say that this carbon is attached to a bromine, this one has a hydrogen, and this one has a hydrogen. Whenever this bromine leaves, remember it takes all of the electrons in the bond, it's going to take all of this. It's going to cause carbon to lose that electron, so then it becomes positively charged. So with carbocations, we need to remember wherever they are, whether it's here or here, that means it's missing a hydrogen and an electron right there. So I'll make certain I was clear on that, because I think I probably wasn't. Okay, so this is how the different ways that it can look. So normally carbon makes 4 bonds because it has 4 valence electrons. So if it has a positive charge, one of those valence electrons are gone. And we can see that manifested Primary carbons look like this, or methyl carbons, primary carbons where you have it attached to just one carbon, secondary carbons where you have it attached to two other carbons, and then you have tertiary carbons. So looking at this, which one of these is the most stable on the top row? That's the tertiary. This one is more stable because it has more carbons there. So in this case, would a rearrangement happen? Would this positive charge move somewhere else? Because it's on the very end. This is the same molecule. It would move to where you have a carbon that has the most carbons attached to it. Oh, that's okay. Brains are weird. Mine was weird on Tuesday. So brains are, they're just weird. Y'all have weird brain days? I have weird brain days. So this one would undergo a rearrangement because this positive charge on this end like this is not stable. So if it could, it'll certainly move to here, but over to this carbon, it's attached to three other carbons. Positive charge on here would be the most stable. So if I were to rewrite this, that way would be a more stable carbocation. This is stable. Yes, because if you think about it, as it moves through, how the arrows would look. Let's draw the arrows. Okay, so if it started here, electrons, and I had a hydrogen here, right? Electrons in this bond would move to here, then they would move to here, and then they would move up over here to this carbon. Yeah, remember, electrons move a lot. So then we could have a hydride shift. That's what we call a hydride shift, where hydrogen moves. So we have a carbocation rearrangement and a hydride shift. Fancy words for positive charge moves to an area where it's more stable, and the hydrogen shifts over where the other one was. Because hydrogen shifts, the positively charged carbon, that rearranges. So this is what carbocations can look like. We can play around with double bonds. We can shift things around. There's lots of stuff we can do in a rearrangement. So this would be vinylic, arylic, benzylic. Eventually, we're going to get there. So it's okay. It's okay. All right. It's still loading. What a great day. Today's a wonderful day in the neighborhood. All right. So I know what I'm going to talk about. I had hoped to use notes. So let me pull up. Oh, what was I thinking? I'm going to pull my phone out and look. If you guys have like the Canvas app, I would suggest If you don't have it, you should get it because it works on tablets and it works on your phones in the event. So I don't know if Alex has an app. Pearson has a dynamic study modules app. So if you have a class that uses Pearson dynamic study modules, you can get that app and put it on your phone and do your homework that way. Yeah, it worked because I've used it before in chemistry. Yeah.
And then it goes to it and it doesn't load at all. It just says not available.
Right, you have to download a separate app for Pearson. Yeah, something like that. A separate app for Pearson will pull that up. Okay, since that has gone to doo-doo, let me pull up. If you have the app, you should be able to pull up the slides. Let me pull up our. It's trying.
No, I mean, on my phone.
Oh,
It's not
okay.
loading there either.
All right. We're in chapter 10. So I was going to talk about the alkene structure because we're getting into double bonds. We're going to get into addition reactions. So if you remember alkenes versus alkanes, y'all know the difference between the two, you remember? Okay, alkene versus alkane. What are the differences? You remember? What does an alkene have that an alkane doesn't? Double bond. So we can have, I need to get a new refill. We can have straight chain alkenes. We can also have, here I'm going to put alkenes on the top. It makes more sense to do it that way. Alkenes, we can have straight chain, and we can have cyclical. Rounded, right? Straight chain alkenes kind of look like this. You can have one like that. Cyclical. Yep, a ring with a double bond in it. So when we're dealing with alkenes, the types of reactions that we put these through are addition reactions. So addition reactions. So the question here is, where could you add stuff? Well, this carbon has, remember, that's okay. Let's try to keep that in the back of our head. Each one of these has a hydrogen on it, right? This one has a hydrogen here. This one has a hydrogen here. So where would be the easiest place? Let's do it that way, to add stuff. Where at? This one? Well, let's see. Okay. Well, we've got a bond here, 1, 2, and there's 2 bonds here, so that's the 3 and 4. Would it be easier to pull off a hydrogen or easier to add stuff to like a double bond? So this is where we can add stuff by breaking up that double bond. Right? We can add stuff there, and we can also add stuff here. So alkenes are super, super useful because if we want to add other functional groups to it, or if we want to add halogens to it, we can rearrange the shape of the molecule just by busting up that double bond. So when we undergo addition reactions with alkenes, we add on that double bond. So we might add functional groups. We can add halogens. We can add OH groups to that. We can add hydrogens. We can add lots of different things to that double bond. Still loading. Okay. All right. So I'm just going to pull some stuff up here so we have images to look at. I want to look at reactions of alkenes. Oh, these are, let me go to the main page. Those are quizzes. Okay. Let's look at alkene reactions. All right. Let's check out their stability. So I'm going to blow this up right here. So, alkene stability. Stability of alkenes increase with substitute. Oh, how do you say that word? With substitute. That is that substitution? I've got substituent stuck in my head. Oh, okay. Substituted. Yeah, okay. So I get confused because when you see substitution, you think the reaction. So that's why I don't like that word like that. So the more stuff that you have attached to the carbons, the more stable it is. Stuff that's other than hydrogen, right? Stuff that's other than hydrogen, the more stable you're going to get. This is the least stable. We can do lots of stuff with this molecule. We can do lots of things with this molecule. This one, bit more stable than this one because we have another carbon here. We have probably maybe a chain of carbons, but we know at least there's one carbon here with other stuff attached to it. Now this is where we come back to cis versus trans. When we're looking at a double bond, are substituents of interest. Are they on the same side or are they on opposite sides? Opposite sides are more stable than same side. Now, when I'm talking about opposite sides and same sides, I'm talking about across the double bond, not on the same carbon. That's the difference. So we have these two groups are on the same carbon on the same side, but that's not across the double bond. So be careful with that. Cis is across the double bond on the same side. Trans is across the double bond on opposite sides. The fancy word for this is geminal. That sounds like I don't know, I think of like going to a club and I hear geminal. I don't know, DJ Geminal coming out. Don't quite know why that word was picked. Some of the other things make sense, but geminal, I'm not certain where that came from. A lot of them is Latin, so I should really dig into Latin and see what geminal means and why they picked that for that particular structure. Then we've got 3 substituents on this double bond, and then we have 4 substituents on this double bond. So the more groups of interest other than hydrogen that you have on an alkene, the more stable it is. Okay, I'm going to erase right here. Are y'all worried about having to work with the public? I know you're not. You already do that. You worry for the public. Ooh, it's hard. Being able to explain the word's gone. Challenging. Being able to explain challenging concepts to the general public is a key role, particularly in medicine, right? Yeah. So communication is actually pretty important for that. Okay, let's talk about conjugation, resonance energy. Please work. Maybe. All right, I'm just going to scroll down until I get to it then. Okay. All right. Alkenes are stabilized by conjugation. So a lot of the times you're going to come across alkenes that have more than one double bond. So we'll use these examples, but I'm also going to use a different example too. So if I have something like this, every other bond is a double bond. This is what we call a conjugated system. And the thing is, I can draw this in different ways. I can draw it, this is where we get those resonance structures, and draw it this way, and it's still correct. What did I do with those double bonds? I slid them over. This one moved to here, this one moved to here, and this one moved to here. The electrons are moving, right? They can also go back the other way. Here, here, and here. So they can slide back and forth between the two. And since they can slide back and forth, if this one carbon gets tired of having the double bond, they can push all of those over to one side. But it doesn't just push one, it knocks them over like dominoes. You have to move all of them. Let's look at this in terms of energy. So here we have but1 E and E. So 1, 2, 3, 4. We got 4 carbons. 4 carbons. So that's our but part of that. We also have 4 carbons here. 1, 2, 3, 4. This is considered more stable than this. This is negative 56.6 kilocalories per mole on those hydrogens. This is negative 30. This is a larger number than this one. We call this resonance energy. So because the electrons are able to move, it lowers the energy associated within those bonds. And since this one can't move and the electrons are stuck in that double bond, it increases the energy associated with those bonds with hydrogen. Yes, if it has one double bond, the electrons can't really move so much from there as easily among those carbons as if it had to. And that's what we call resonance energy. Let me slide up a little bit where we're looking at cis versus trans and the energy associated with those bonds. All right. So we have, again, but 4 carbons. These two are caught up in a double bond. And then we have these 2 methyl groups on the same side. This could be oxygen. It could be any functional group. You have 2 functional groups on the same side. You're dealing with, let's see what we got. This is a higher energy cost. Well, is it or is it lower energy? Kilocalories per mole. Lower energy, higher energy. That's more stable. Those numbers are throwing me off. Are they throwing you off? Okay. The difference in stability, rounding up generously. What does it say? Heat of hydrogenation data. Oh, call it its proper name, 1,2 strain. Okay. If it's higher energy, then that means it shouldn't be as stable. This is negative kilocalories. Okay, I'm going to ignore the values for now because I think that's going to get confusing. Let's look at it in terms of electron density. All right, I'm going to erase right here. Let's look at it as a more conceptual, type of thing. So if I have something like this, and I have CH3, CH3, and then I've got hydrogen here, and the hydrogen here. I've probably made this bond too big. Let me make it a bit smaller. If this was a larger molecule, if I had even a bromine on here, bromine's a pretty big atom. We've got a really big atom here, and then you have this whole thing going on here. Because remember, you got a hydrogen, and a hydrogen. So you've got a lot of electrons right here, just on this bromine. And you've got electrons in here, electrons in here, and electrons in here. Are they going to be attracted to each other, or are they going to repel? They're going to want to repel. So this is less stable if for nothing else, electrons are close together. Okay. They're on the same side. So you've got electrons here, and then you've got one here and here. It's a bit more like this, actually. Here and here. And you've got electrons here, 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 and here, right? Yep, on the same. It wouldn't be a problem. So this is a cis configuration. A trans configuration could be like this. Right? More stable because electrons are further from each other. You put a lot of strain on this double bond when you have two groups being on the same side because those electrons are really close together. You've already got a lot of electrons here, 4 electrons there, right? You got electrons here and here. You got a very one side heavy electron setup. This one, you got electrons here, electrons here, electrons here, kind of more spread out, right? So if your brain starts to get muddled, think electrons do not like to be near each other. And if you have to think, is this structure stable? Look where all the electrons are. You got two bulky groups. These are pretty bulky. You got a carbon with 3 hydrogens around it, a carbon with 3 hydrogens around it. That's a lot of stuff on one side. And it's a lot of electrons when you consider the ones in this bond, the ones here and here. Then when you look at this, they're more spread out rather than being right on top of each other. So the same thing with this. Look at this situation. So here we've got an R group. So we got all these carbons with these hydrogens. There's a carbon here with 2 hydrogens, carbon, 2 hydrogens, carbon with 3 hydrogens. Then we have a methyl group here. This is all on this side, really bulky, lots of electrons close together, less stable than if you spread them out. So more stable is the trans formation, less stable is the cis formation. Really? I'm going to reset it. I think I just pulled my back. Y'all getting old sucks. Let me try again. Were any of y'all able to get in on yours? On the app, okay. I really wish they would just go ahead and outsource whoever's in charge of our servers to like a company that knows how to handle it. Because this happens more often than it should, but I get it. Stuff's hard. All right, so let's see. Let me scroll back up. All right. Okay. All right, that's all I'm going to talk about there. Let's go back to here. Come on. That really just pulled my back. Reaching. Ah! Okay. Let's look at alkene reactions. All right. Let's look at ENZ notation. I think we talked about this a little bit last semester, but we're going to go back into it in more detail. Okay, so we use E and Z notation when we're dealing with double bonds. Z is kind of what we consider for substituents that are on the same side. E is where we consider substituents that are on the opposite side. Zusammen, I'm not certain what the etymology is of that word. Does that sound German? Zusammen. So that we have the mnemonic the same side. E is opposite side. So if you remember that one, you should be able to get this one. Okay. Cis and trans isomerism. Remember isomers, there's different types of isomers. There's constitutional, there's cis and trans. Here we go. So when we're dealing with rings in the dash and wedge examples, we look at cis 1,2-dichlorocyclopentane. And then we've got trans. They're going in opposite directions. Trans 1,2-dichlorocyclopentane. So these are both coming out towards us. This one is coming out towards us while that one's going in the back, right? Their physical properties are vastly different. Just the movement of the direction of that chlorine in comparison to the other one gives it vastly different properties. Okay, so let's look at cis and trans for this. We need two conditions if we have cis and trans isomerism in rings. Two and only two carbons, each bearing non-identical substituents above and below the ring. Two carbons have at least one of those substituents in common. So we saw that C1 and C2 each had non-identical substituents, that's hydrogen and chlorine, above and below the ring, and they had at least one substituent in common, hydrogen and chloride. Let's look at this case. We can use cis and trans so long as the two carbons have at least one identical substituent above and below the ring. So in this case, it's hydrogen. These carbons both have a hydrogen, so we can use cis or trans. So we've got hydrogens going back into the board and these coming out, or hydrogens coming into the board, coming out of the board, and the methyl and ethyl group going back into it. So when we're using dash and wedge, remember, dashes are going back, wedges are coming forward towards us. Here, this is our trans setup. We've got hydrogen coming out, hydrogen going in, ethyl group coming out, methyl going in. That's one trans configuration. Here's the other one. We just swapped which direction that they were going into the board or coming out of. So we can use cis and trans in those contexts. So here, we don't have, let's see, only one carbon with two different groups above and below the plane. This isn't possible. We can't use cis and trans in these cases because this one is just pretty much the same molecule It's just flipped over. This hydrogen starts out coming out at us, but if we flip it over, it's going back, and the methyl group is now coming out at us. So we don't need to use cis and trans for this. It's the same molecule. Here, too many possibilities for cis or trans. So we have 3 or more carbons with 2 different substituents above and below the plane. So here we've got something different here, something here, and something here. We have too many carbons that have too many functional groups on them, right? Too many possibilities. So for this, we would use the RS. All right. So here, we're kind of going back with conformational isomers versus geometrical isomers. So we've got, these are identical. All you got to do is turn them around. This one has free rotation. Y'all remember that single bonds that can spin around? So free rotation, we call that something different. And when we start introducing double bonds, that's where we don't have that free rotation, and that's when we start really looking at cis and trans. So here, this version stuff is on the same side of the double bond. This is not the same as trans. You can't flip this around and make it look like trans. You have to make it undergo a reaction to get it to do that. There's no twisting here. Same thing with this. You can't twist and make it look like this. Because the changes are happening around the double bond, you have to make it undergo a reaction. Okay. Let's see. So this is the same molecule drawn from 2 perspectives, just rotating the entire molecule 180 degrees. Let's see. Let's look at for when cis and trans fails. So here, how do we do cis or trans with that? We really can't, can we? This side isn't the same, right? There's nothing the same. There's no hydrogens there. These carbons, these have 2 different things. And this carbon has 2 different things from that. They're geometric isomers. They have the same formula, but they're put together completely differently. So we can't use cis and trans. Yeah, because this would still be C, let's see, 1, 2, 3, C3, H3, FBrCl. So it'd still be the same, but how they're put together is different. So we would name it something different. And that's where we get into E and Z. So here, let's see. We have to look at ranking each group. Okay. Now, when we're talking about a pi bond, we're talking about a double bond. Okay. So if you see pi bond in terms of EZ, it's talking about the double bond. So we rank the 2 atoms directly attached to the pi bond by atomic number. Higher atomic number, higher priority. So in this case, we're dealing with halogens. Halogens are going to take priority over the carbon, right? Because they have a higher atomic number. So we draw a line down the middle in the double bond. We have our carbon on this side and our carbon on this side. So between the two of these, bromine or fluorine, bromine has the higher atomic number, so that gets precedence over this one. Fluorine has a higher atomic number, gets more precedence than carbon. So we number which ones are important, well, more important, priority. I guess they're all important, just they do different things. The atom with the higher atomic number is priority. So over here, same thing. Bromine's down here. Fluorine is up here. Here we got chlorine, and we've got our methyl group. Okay. This is what we do. So the alkene, where the highest priority groups are, if they're on the same side, it's Z. If they're on opposite sides, it's E. Easy. Let's write out in steps. Let's write out in steps what we're doing for this. Easy notation, right? Okay. One, if the carbons with double bonds do not have similar functional groups or the same functional groups, use EZ notation. Okay? Now we draw a line down the middle of the bond. Okay. The carbons, let me see. Trying to think of the best way to word this. Carbon on the left side of the bond, we'll just say that. You could do left or right first. I'm just going to go this way. Carbon on the left side of the bond assign numbers for groups, let's say groups according to priority. I'm going to draw pictures to go along with this. Carbon on the left side of the bond assign numbers for groups according to priority, meaning highest atomic number gets the number 1. Highest atomic number gets number 1. Then the next one is number 2. Then the next thing we do, assign numbers of priority for groups on the other carbon. Same thing. Highest atomic number gets number 1. If number ones are on the same side of the double bond, if number ones are on the same side of the double bond, call it Z. If not, if on opposite sides of the double bond. Call it E. So if carbons with double bonds do not have similar functional groups, use EZ notation. So let me just make up another one. So let's say we got a fluorine here. Let's say we got an OH here, okay? Let's say we got a methyl here. And let's say we got a bromine here. Let's do, is it E or Z notation? We draw a line down the middle, right? Which one is higher priority, bromine or methyl? What do you think? Which one has a higher atomic number, bromine or methyl or carbon? Bromine. So that gets number 1. And this one's number 2. All right, here. This time we're looking at oxygen and fluorine. Which one has a higher atomic number, fluorine or oxygen? Fluorine. Number 1. So is this E or Z? It's E. It's easy, right? I've never heard this before. I don't think I've ever heard that before, so that's funny. That's how we do that one. How do we break ties? Okay. Each side of the alkene is attached to a carbon atom. Okay, so in this case, we got a tie going on here because we got a carbon here, we got a carbon here, we got a carbon here, and a carbon here. So if we have a situation like this, we place a dot on each of the 2 atoms you're comparing. So we're comparing this one and this one, these 2 right here. List the 3 atoms each atom is attached to in order of atomic number. So you're comparing a set of playing cards. So here, we're looking at these 2 carbons. We don't know which one gets the 1 and which one gets the 2. So we look, okay. This has got a carbon here, a carbon, hydrogen, hydrogen. This one has a carbon with 2 hydrogens. Hydrogen, hydrogen, this is over here, and this has got an oxygen, okay? Now we gotta go, okay. After we figured out what's going on here, this one, okay, this carbon, the next thing to it, has an oxygen. That has a higher atomic number than the next one here, which is a carbon. So you have to start going up the chain. So here, both of these carbons, pretty much the same. We go to the next carbon. Okay, this one's got a couple carbons. That doesn't take priority over that oxygen. So this is the 1, and this is the 2. So in breaking ties, go further down the chain and see if you find an atom that has a higher atomic number than the ones over here. Okay. Woo! 4E6Z117 trichloro 4,6 dimethyl 146, known as triene. Oh, so it's 9 carbons with 3 double bonds, and then we've got a bunch of functional groups here. I probably won't do something like that to you. I mostly just want to make certain you can follow the basics. Okay, so here, across this double bond, we have 2 different things here. So we would have to use easy for this situation. We would have to use easy for that situation. And we would have to use easy for this situation, I think. Yeah. So I wouldn't give y'all a long one like that. So how we deal with tiebreakers, how we do easy notation. Okay. Oh, it finally pulled up. We've talked about alkene stability. Really? You really signed me out. Watch it. Is it going to load? I've given up on this for today. I'm giving up on this for today. All right, let me look at. Oh, I set my phone over here. Okay, let me see. I've given up on that today. All right, so the notes talk a lot about fatty acids. And we'll just have to do electrophilic addition. I really need pictures to pull up. I don't want to get into this without having access to Canvas. All right. Okay. Come on. All right. Now I'm going to pull stuff up here. Yay. Okay. So our main objectives for chapter 10. Oh, we do need to talk about degrees of unsaturation. I'm going to get into the addition reactions. I'm going to do that on Tuesday, and then we'll have our quiz on Thursday, covering all the stuff for Unit 1. So we'll spend all day on Thursday working on that quiz to help you out with that. Okay, so we're going to cover the reactions on Tuesday. Now let's talk about degrees of unsaturation for hydrogens in a carbon compound. There's a formula that we use to determine, it's like a basic standard formula that we see with organic compounds. It's CnH2n. Let me see if I can pull that up on our notes. Now that they're working. Okay. All right. Okay. It does this every time it updates. It does that. Okay. So there are some pictures on here that might be useful to help you with easy configuration. You want to go back through and look at it. Okay. We're going to worry about reactions later. Again, some cis trans. How to draw that? Hold on. I need to make this part bigger. Not that, not that, not that. I want to talk about the degrees of unsaturation. I think I'm getting electrophilic addition. I think I've gone too far. Woo! So many reactions, guys. All the different ways to put carbon together. All right, I think maybe I went too far. Preparation of alkenes. It's 7 on the notes. There you go. See? Okay. Thank you. So an acyclic alkene, CnH2n. So you have twice as many hydrogens as you do carbons. So cycloalkenes also have that same formula. So each pi bond, each double bond removes 2 hydrogens. So here, we've got possible C4H6. So we've got 2 rings, or we've got 2 pi bonds, 1 ring and 1 pi bond. Let's see. So degrees of unsaturation for molecules containing heteroatoms. Those are atoms that are different from each other. So you ignore the oxygen atoms in the molecule. It has no effect on unsaturation. Do y'all remember the difference between saturated versus unsaturated? Yes. Yes. You need a test? That's okay. I've got some printed out. I'll bring it to you. I'm almost done. You're welcome. All right. Saturated means all carbons are covered in hydrogen. Unsaturated, that usually means you have double bonds with fewer hydrogens attached. Okay. So, if you have something that has other than carbon and hydrogen, you have oxygen, halogens, any of that, we ignore the oxygen atoms and we add the number of halogens to the number of hydrogens. They're equal to hydrogen because hydrogen can only make 1 bond. Halogens can only make 1 bond, right? So you subtract 1 hydrogen for each nitrogen present, because nitrogen's 2 connections allow that extra hydrogen. So something like this. We've still got our 6 carbons. We ignore the oxygen. Let's see. And then we add 1. So add number of halogens to the number of hydrogens. They are equivalent to hydrogen. I don't know. There's 3 halogens there. Oh, wait. Yes. You add the number of halogens to the number of hydrogens. They are equivalent to hydrogen. Yes. Because N makes 2 bonds. Nitrogen makes 2 bonds. So you subtract 1 hydrogen for each N present. So we've got 10 13. That N, we take away 1. So we have 3 halogens here. Those count the same as a hydrogen. So I add that to there. That's 13. There's a nitrogen. Take it away. So now it's 12. Okay. Yes. So remember, halogens are iodine, chlorine, fluorine, and bromine. So this is the same as 1 hydrogen. Each one of these counts as a hydrogen. Because when we're counting for saturation, halogens make 1 bond. Hydrogens make 1. Yes, you just ignore oxygen. Halogens make 1 bond, so do hydrogens. Nitrogens make 2 bonds. Okay, so we subtract 1 hydrogen from that because nitrogen make 2. So when we're doing degrees of saturation for each nitrogen, we subtract 1 hydrogen. So for this one, number of carbons stays the same. Yay, just write that over there. Saturation has to do with if every carbon is covered in something. So when we're getting with unsaturated double bond stuff, yes, yes. So we've got 10 hydrogen, we ignore oxygen, we add 3 to it, so that's 13, and subtract 1 because of nitrogen. I'm gonna, yeah, I'll write your test similar to your quiz. So we'll have all day on Thursday going over and spending time on the quiz. And then we'll have your test on that following Tuesday. That'll give y'all plenty of time. So I'll grade the quizzes on Thursday when you turn them back in, and I'll give you the answers. And then you can go back through and use that to help you with your exam. So next class, if Canvas works, I'm going to just download notes and I'll put it on my thing and stick it up in here. We'll talk about all the reactions and just knock that out.